All right, so here we go. We're going to go over the second example problem. In this problem, there are two masses, both at rest, which means it's in equilibrium. All the forces are balanced. The forces on the 5 kilogram mass are balanced, and all the forces on the 4 kilogram mass are balanced. You'll hear me say this a lot throughout the series of problems here. Two masses, two problems. Okay, keep each one separate. All right, the first part is to draw a free body diagram, or to draw and label all the forces acting on the masses. So here we go. If we say this is our 5 kilogram mass over here, well, what forces are acting on it? Well, Earth pulls it down. So straight down, gravity, force of gravity equals mass times the acceleration of gravity. So that is 5 kilograms. That's the mass. The acceleration due to gravity is 9.8 meters per second squared. Do that arithmetic, you get 49 newtons. Same problem from example problem number 1. Now it's not moving down, even though Earth is pulling it down, so the table must be supporting it. Try your best to make this arrow and that arrow the same length. That's called, the support force is called the normal force. And then it's attached to a rope over here, so there's tension in the rope. But again, it's not moving to the side, so there's got to be a force back this way, preventing it from moving. That's friction. So there are 4 forces here. Here, you might be able to recognize this pretty quick. There's only one force down and one force up. So these two things, it's not moving up or down. That normal force is also going to be 49 newtons. All right, always things we want to do is you want to say sum of the forces in the x direction equals mass times acceleration. Since it's at rest, it's in equilibrium. Acceleration is 0. If the acceleration is 0, the sum of the forces equals 0. Well, what forces are acting horizontally? The sum of the forces in the x equals 0. But what equals 0? The force of tension plus the force of friction. The force of friction is to the left. Because that's left, that is negative. So really, that's going to be a negative force the wrong way. So you could say the sum of the forces in the x direction equals the force of tension plus a negative force of friction, or minus the force of friction. We don't know what either of those two forces are just yet. But always separate these, do just the horizontal forces, and then you want to do the vertical forces. Sum of the forces in the y direction equals ma. This box is not moving up or down, it's at rest. So the sum of the forces, get rid of that. So the sum of the forces in the y direction equals 0. Well, what forces are in the y direction? The support force is up, and we also have gravity pulling down. Again, this is down, which means negative. So we could say the sum of the forces in the y direction equals the normal force plus a negative force of gravity, or you can say force of y direction equals the normal force minus the force of gravity. We calculated the force of gravity a moment ago, so some of the forces in the y equals the normal force minus 49 newtons. We know the sum of the forces is 0 equals the normal force minus 49 newtons. What minus 49 equals 0? The normal force equals 49 newtons. That's the long way to figure out something pretty obvious. It's not moving up or down. These forces must be balanced. If the weight of this thing, the Earth's pulled down, is 49 newtons. The table is supporting it that same amount. In this case, it's the same amount because there's no other forces up or down. All right, so that's pretty simple. That's the first part. We also have two masses, two problems, right? Two masses, two problems. So don't forget, you can't just do this once. You have to do this again over here. So the 4 kilogram mass has the rope pulling it up, the force of tension, and Earth is also pulling this one down. Again, the force of Earth pulling down is mass times the acceleration of gravity, which is going to be, I'm just going to scroll this up a little bit. All right, 4 kilograms multiplied by 9.8 meters per second squared. 4 times 9.8 is 39.2 newtons. I think this is obvious, again, what the force of tension is. Always, there are no forces in the horizontal, so to do the sum of the forces in the x is kind of redundant. There are no forces in the x value. The sum of the forces in the y equals ma. It's not accelerating, so that equals 0. But what are the forces? So the sum of the forces equals 0, but those forces in the y is going to be the force of tension plus the force of gravity. Again, because the force of gravity is downward, we're going to consider that negative. So sum of the forces in the y equals the tension minus the force of gravity. 0 equals the force of tension minus 39.2 newtons. The force of tension equals 39.2 newtons. So up here, this is equal to 39.2 newtons. That's actually parts 1 and 2. So we figured out, we drew with our free body diagrams. Our free body diagrams, pretty obvious. Okay, the first free body diagram looks like this, these 4 arrows. The second free body diagram looks like this, these 2 arrows. And part B asks to figure out the force of tension acting on the string. The force of tension on the string is 39.2 newtons. I'm supposed to zip into a box there. There we go. Force of tension is 39.2 newtons. Same string, same rope, same string, same tension. So over here, wrong way. Sorry, guys. If this tension up here, switch colors a little bit. Come back. If this tension over here is 39.2 newtons, this tension over here is 39.2 newtons. Same rope, same tension. This is 39.2 newtons. That just helps us a lot figure this out. Okay, I'll stop here for now.